Thank you. There's currently a special group of engineers and scientists who believe we can solve some of the Earth's problems far above the Earth. And no, I am not talking about prayer. This group, the International Space Elevator Consortium, has been meeting since 2008, researching and writing about the potential for, as they say, a transformational leap for human movement far into space using space elevators. The president and director of this team is our speaker today, Dr. Peter Swan, also known as Pete. Pete has pages of credentials, some of which you can see online, but I'll only share a few that have impressed me the most. He is a PhD in mechanical engineering, focusing on space tether dynamics from the University of California at Los Angeles. He's a lecturer and faculty associate at the Osher Lifelong Living Institute at Arizona State University. And he was a keynote speaker last month at the International Astronautical Federation in Paris, France. He's written numerous books, many on space elevators, and that's how I met him. I've been reading his material for years as research for a novel. This spring, I contacted ISAC to request a review of what I had written about space elevators. To my amazement, Dr. Swan responded. I was so excited to receive his feedback. I'm even more excited to introduce this amazing man to our HASP group today. Please help me welcome Dr. Peter Swan.
Well, thank you, Joyce. I really had fun working with a science fiction writer, especially with a lot of imagination and then the characteristic of finish it mentality. Great attributes for a mega project, which is where I am. I need to complete this huge endeavor within a reasonable time. Indeed, I believe I can. With 50 years of space engineering development background, I believe the space elevator is doable. Now the challenge for you during this hour and a half. Can we fulfill your dreams for space? Or even more applicable in the timelines, can we fill your granddaughter's dreams? My answer is, of course. All we have to do is beat the gravity well. Okay, just a quick note. I like to challenge a student, and you guys are all students. It's part of the problem here. We all have students and we get to have fun with them. Anyway, the challenge to the student is to reach beyond where they are thinking. I do this by having too much information and too fast. There are 2 points there. One is there's no test afterwards. That's the first one. And the second is these charts are available. Ian has them, and you can go over them inch by inch if you would like to later, or use them as you would like. They're open for your pleasure. But the bottom line is we're dreaming of space. Holy Toledo, everybody's been doing that since you were in the cradle. And so I have an idea here that we've been developing, which is to take a space elevator instead of a rocket. And I'm going to explain why that is. Also, I think I might stop about a third of the way through and answer 1 or 2 questions along the way. So go ahead and put your questions in early, and then Ian or Joyce will identify 1 or 2 questions we'll answer then, and then we'll continue. I always like to break it up a little bit. So anyway, here we go for a little ride. Let's see. The first thing is, what is a space elevator? Well, the space elevator is relatively simple in concept. We run 100,000 kilometer tether, 1 meter wide, molecules thick, 100,000 kilometers straight out from the equator. And what it does is it rotates with the Earth. So the very end of the tether, the apex anchor, acts like a rock on the string around your head as you rotate it around your head. And that's all it is. It's a very simple concept. Now, just to put it in perspective, if you look on the lower right, we have the radiation environment for the Earth, and look how small the Earth is compared to this mega project. And that's what we're going to talk about. I believe we can do that. I mean, it's not that hard. You unreel a string of 100,000 kilometers long. You know, they make aluminum foil and saran wrap at huge rates. And so we can probably do this also. Okay, well, what do we really mean by a string that goes all the way up? What we're going to do is have tether climbers raising from the surface of the earth with electricity. So we don't burn anything in the atmosphere. We don't leave any debris in this lower orbits or anything like that. So it really is a green road to space. And what we're planning on doing is having two next to each other, one up, one down, or both up if that's where the money is. It's going to be a commercial effort. This will all be commercial. And so we go up to geosynchronous. Well, we know we can make a lot of money at geosynchronous because that's a very valuable region that stares at a hemisphere of the earth. And we've got lots of communication satellites and weather satellites, all that kind of stuff. And then you keep going up to the top. And that's a unique characteristic that nobody else has, which is the ability to be attached to the earth, go at like 15,000 miles an hour around the earth. And you release from there, you can go to Mars in 61 days with no rockets. It's just toss it out there like a rock on the end of your string around your head. Okay, what we're going to talk about is the transformational capability of a space elevator. Now, what I would want to remind everybody is I love rockets. I was in an Apollo launch. I was testing rockets. I've seen them blow up. I've seen them do all kinds of good things. The real kicker is rockets are important. They do things a space elevator can't do, like move people through radiation belts rapidly and rendezvous and land on planets and all kinds of things. So we need rockets. We want to have a dual space access philosophy. So this little image on the left was done by a summer intern of mine. She was an engineering student, senior at University of St. Andrews, or was it Edinburgh, one of those anyway, but she's an artist also. So she figured out what we wanted to talk about and actually painted it. So it came out very nicely. Okay, dreams. How close are dreams? Well, guys, this one is en route. I'm going to give you the details on the next chart, but there's a gentleman for Japan who has paid Mr. Musk to send him and 7 of his closest friends around the moon. He's already paid the money. Mr. Musk is planning on doing it. This is going to happen in 2023. Wait a minute. That's next year. Holy schnuckers. When we talk about dreams in space, the space world is expanding so rapidly, it's hard to comprehend. Now, where does that come from? It comes from the commercial imperative. Mr. Bezos is putting part of his $180 billion. Mr. Musk is putting part of his $270 billion into space. Why are they doing that? Because they have philosophy that they want to move humans off planet. So that's a big task. This is just one step to show that it's relatively easy. We're going to go around the moon and come back with just a commercial activity. What happened is this gentleman, the Japanese entrepreneur, said that he wants to go around the moon with artists to express the intriguing aspects of spaceflight and leaving the planet. So his requirement for the artist, he's paying the bill. The requirements must provide an inspiring global university art project at the end of their mission or soon afterwards. So we're going to have, a bunch of artists come back from their trip and express what it's like to leave the planet. An intriguing concept. I just thought I'd bring out, this was a dream 10 years ago. Now it's reality. They're going to do this next year. Okay, well, let's reach a little further. Let's put 1 million people in a cylinder that's rotating so you can have, lands on the outside and stay on the outside. This is a cylinder 4 miles long and about 1 mile in diameter, and we're going to put 1 million people in there. That's been the vision of the National Space Society since about 1965. And they're still thinking about this. But, the problem is, I asked the people in the NSS how much mass they're going to have to move. They never mention that it's 10 million tons to the altitude of the moon. It's an amazing dream. But that's one of the major dreams of a portion of American thinkers. Here's a bunch of ideas. The British Interplanetary Society wants to go explore and go beyond Mars. Mr. Bezos wants 1 million people living in space and working productively. Mr. Musk wants to have multi-planetary. He wants to put people on Mars. These are actual dreams that are being planned and executed out there. And then, of course, there's NASA, who is going to put women's boots on the moon in 2024 or 2025 or 2026. But they're going to do it. They have the equipment, the rocket, and everything else. And the European Space Agency says we're coming along. So they're building some of the hardware for the rotating space station around the moon, which would be a staging point for going down to the moon. So there are a lot of dreams out there that are real, that are being executed. They're no longer just science fiction dreams. These are happening. So the dreams of humanity to move off planet are real. Mr. Bezos has recently announced that he's going to have a commercial low Earth orbiting space station for research. And people are going to pay him to go up there. So these things are exciting to see, but they all have the basic flaw, which is they have to use rockets. Here's some pretty pictures with the NASA one in the middle, the Space Launch System. It's a humongous rocket that will be able to take us to the surface of the moon. It is going to be amazing. Mr. Musk wants to go to Mars. There's a whole idea going to the moon. I mean, it is exciting to be out in the space arena today because it's going so fast. And the reason it's going fast is the commercial imperative. Here's a pretty picture. Mr. Musk wants to have this on Mars. Can you imagine 1 million tons to Mars? Wait a minute, 1 million tons. I want you to remember that number because we're going to talk about it in the middle of the presentation here. Okay, the Mars colony, we're starting off. But one of the things we're going to do first is go to the moon. This is a government program to go to the moon. It is remarkable. Remember, I love rockets, and this is a massive rocket that is really amazing. It's $2 billion a launch, and it's not reusable. There's nothing in there that's reusable. Now, it turns out that I put down $18 billion development. Somebody recently said it was $80 billion, and I've heard $60 billion. It's been a lot of government money spent on this. I'm just pointing that out. But it is a phenomenal rocket, and it will deliver women and men to the surface of the moon for the Americans and the Europeans and many other nations that have signed up to go to the moon. So it's going to be an amazing effort to put people on the moon in the relatively near. I mean, this decade we'll have multiple flights to the moon. Now, one of the things that happened along the way was NASA said, I need help getting from our space station that's around the moon, they call that the gateway, down to the surface of the moon. So they had a competition with 3 players, and they had designs, and they said they were going to award 2 contracts. Well, they ran out of money, so they decided they would only pick one. It was not Mr. Bezos's pretty little blue moon lander, which he displayed at the Washington International Astronautical Congress 3 years ago. And I watched around and nobody was looking. So I went beyond the rope and actually touched it. So I've touched that vehicle. It's real. And there was another NASA driven contest, but the winner was Mr. Musk. He won by lowest cost and the most capable system that would go from the Gateway space station to the surface of the moon and return. So he's taken his Starship that he had planned to go to Mars with and adapted it a little bit to be an up and down vehicle for the moon. So we have a winner there. Well, Mr. Musk said, wait a minute, we can't do that. You said you were going to award 2 contracts, and he objected to it legally. And the legal people said, no, NASA could do that. NASA was okay. So we have one winner. And so Mr. Bezos says, okay, you won. Now, Mr. NASA, I would like to provide a vehicle to go up and down from your gateway to the surface of the moon for free. Wait a minute, think about that a little bit. Mr. Bezos says, I competed and I lost, but it's okay. I'll do it for free. So he wants to do that Blue Moon lander in parallel with Mr. Musk lander and supply the facilities for NASA and others to land and live on the moon. So we have a two-vehicle race now. Well, a year and a half after all this kerfluffle occurred, NASA came out and said, after Mr. Musk's first three landings, we'll compete for future commercial capability. So Mr. Bezos wins in the long run by investing a lot of money, but then he can compete for the service contract going up and down. So it's a very interesting world right now, going up and down to the moon, going to Mars, all that kind of stuff. The dreams are out there and they are being executed. Okay, this is the way Mr. Musk can get to the moon directly, though. So he's got his Starship, which is the one he's designing to go to Mars, and he can actually refuel it and go to the moon and land directly. Wait a minute. This conflicts with the NASA Space Launch System. The NASA Space Launch System is supposed to take Americans and Europeans to the surface of the moon. Wait a minute. Mr. Musk says, no, I can do it commercially. Hey, this hadn't been solved. This is all up in the air. It is hilarious if you sit back and look at it, but it's really a remarkable activity. And these are all coming from the dreams of these players in space. They want to, and fill in the blank, and they're doing it. So it's really interesting. But what I want to point out to this crowd is, I've mentioned mass 3 or 4 times. Let's think about it. Here are some of the dreams. Now, we haven't talked about these, and I'll just quickly go over. The bottom one is that spinning cylinder at the altitude of the moon. That's the 10 million tons. And then going up the list, Mr. Musk wants to have 1 million tons to Mars. And the Moon Village, which is kind of like a European led, but Americans are playing in it. We want to have 500 million tons on the moon. Oh, and then there's let's save the atmosphere and provide space energy from space and eliminate coal plants for power. So we want to contribute base electrical power around the globe and eliminate coal plants. A relatively big job, 5 million tons to geosynchronous. And then there's the idea, hey, we've got global warming. Why don't we just block a little bit of the sun? So there's the idea of a sunshade between the Earth and the sun. And we could cool the Earth by 2 degrees is what their idea is. Now, that was an idea for Professor Angel at the University of Arizona like 40 years ago. But there was no need in those days. We didn't need to have a cooling of the Earth. And now there's a need, a perceived need that we need to do that. And now this system is coming back up. But look at the numbers, 20 million stinking tons, well beyond geosynchronous. So I keep mentioning this mass thing. I know it's a bothersome thing for you guys, but let's take a history lesson here. To get to low Earth orbit, we consume 96% of the mass that starts on the pad. Let me say that again. We only get 4% of all that stuff on the pad to orbit. Okay, it's all burned up or it's tossed away in the history. Mr. Musk has come along and he says, I can reuse my rockets. So, okay. So the rocket shells and the engines are going to be reused. He still does not get more than 4% to geosynchronous. Now it's cheaper. To LEO, low Earth orbit. He still has to bring the rockets back down and land them and refurb them and everything, and that'll be cheaper. He can do it more redundantly. He can have a lot more launches. He's got more space on this thing. All that is good. Mr. Musk is doing a fantastic job. Oh, by the way, Mr. Bezos is doing the same thing. He's just not there yet. He's about another 18 months and he'll have his own reusable big rocket. So you can go to LEO with 4% of the mass and reuse all that stuff. That's good. So it'd be cheaper, but it's still the rocket equation eats you up. To go to geosynchronous, way up there where the productive commercial communications and weather satellites are, you only get 2% up there. And the mass delivery to the surface of the moon is 0.5% of the pad mass. Think about that a little bit. If you ask somebody to deliver a Toyota to Los Angeles from Japan, and you had them deliver the Toyota to San Pedro, and then take the ship out to Catalina Island and sink the ship, that's what we're doing. That's what we're doing. It's a bummer. Anyway, so we've got these numbers down at the bottom. By the way, it took me 6 months to come up with those numbers on the bottom. We have only put up 22 million kilograms. By the way, the rocket community only talks kilograms. They don't talk tons. So that's 22,000 tons in the history of humankind to put stuff in orbit. Oh, wait a minute. 22,000 tons. What have we been talking about? We've been talking about million tons. So historically, let's just say 25,000 tons. You know, that's not a very big number. And why is that? The stinking rocket equation. Bummer. Here's an example for the Saturn V. That's what we put on the surface of the moon. 0.5%. By the way, putting stuff on the surface of Mars is a little less than that. It's like 0.2. So Mr. Musk wants to put 1 million tons to Mars, and it would be at 0.2% of the mass on the pad. So you do the division and come out with that. It's a lot of tonnage on the pad in Texas or wherever he's going to launch from. So the conundrum of rockets is, bummer, we have lousy delivery statistics. I mean, really lousy delivery statistics. FedEx would not take this job. I mean, it's just silly. They wouldn't even think about this. Amazon would charge you extra for this. In fact, Mr. Bezos is going to be providing the service to the surface of the moon. I've often wondered, if you're a prime member of Amazon, you get delivery free. That'd be an interesting question. But anyway, an intriguing conundrum we have gotten ourselves into. I guess I'm supposed to say an intriguing conundrum, Ollie. But anyway, so the colonization of Mars. We want to go there. Mr. Musk has said we're going to put, 1 million people on there in his lifetime, and he's going to go to Mars himself. It's a big task, but he is off and running doing that dream. So the movement off planet is going to happen. I have no doubt about it whatsoever. So, NASA is going to put women and men on the surface of the moon. So my question is Mr. Musk going to go fly around Mars with his vehicle before we put people on the moon? I don't know. I don't think he'll put people on Mars first, but he could land on the surface of Mars and come back as a test run before NASA gets their people on the moon. So it's a race, a little race, not much. Now, I often like to mention this to us people that are doing mega projects, that just a week or so, or 9 weeks before Orville and Wilbur flew, the New York Times editorial predicted that flying machines would not fly for 1 million years. I mean, that's, the big scientists in New York City thought that flying machines are the stupidest thing you ever heard of. So, there are people that are skeptics on every system. And so I like to remember that statement when I'm dealing with space elevators, because there are a lot of people that might not quite buy into it. But of course, why would you buy going into Mars too? I mean, this is tremendous opportunity to go expand. So how do we do this going to Mars? We have something like this. Well, we had the pioneers, they're called the Apollo program. And then we have tourists going up and down in low Earth, not even getting to orbit, just going up past the 100 kilometers altitude and getting astronaut wings. And then we have to have some type of way to get there and be, somewhat safe, like a low Earth orbiting space station or something like that. Then we get those explorers. And they're going to be real explorers going to the moon. They've got to find water so they can live. They go to the Mars, they got to find water so they can live. On Mars, they've got to be able to take the atmosphere and create fuel. So they got to have a Texaco station up there on Mars first. And so that should be a challenge. And then you have the settlements after that. So we've got a laid out historic path, and we know how to do this. We just have to make the transportation vehicles work. And that's the puzzle that we're in right now. So jobs you can do on Mars in the future. They've been talking about this. A lot of scientists are talking about it, but essentially it's survival. Let's find the water. Let's have some habitats we can grow some, food in, stuff like that. A lot of survival aspects initially. This is the way Mr. Musk is going to go there. Now, I hasten to add, it's going to take him 5 vehicles to get one vehicle that can go to Mars. So you've got to refuel, 2 of those are refuel, and then you have the resupply, and then you got to bring the people up. So they have 5 stinking vehicles to refuel. And he wants to do 1,000 launches a year. So ask yourself about environment there. And then he gets to Mars, and then to come home. By the way, he believes he can come home. This is not a one-way. He has to develop a Texaco station. All you have to do is have water in the atmosphere, and you can make fuel, so you can come home. So it is a remarkable concept, and he's well on the way to do it. But there's a puzzle out there. Many people have talked about going to Mars, but they keep talking about it as if it's a good place to go. It is inhospitable. It is going to be hard to figure out how to live there. It's a long way from the sun, so solar arrays don't work too well. You have to find some lava tube or something like that, or cavern to hide in to get away from radiation, because they don't have an atmosphere of any significance. So there's a lot of puzzles in this dream to go there, but we are doing it. We are going. So the question before we have more questions is, why should humanity move off planet? And, I think there's 2 or 3 reasons. One of them is survival of the species. The dinosaurs did not have a space program, so they passed away. We need a dispersion of the species so humans can survive. Of course, that also implies that humans have value, but that's another philosophical question we could pursue some other time. But we would benefit humanities for all kinds of things, providing hope, providing more technologies, providing supplies. I mean, it really will benefit humanity in the long run. So we need to do that. There are a lot of reasons in the sense of threats to our planet. And, we all know what they are: extreme climate change, asteroids, all kinds of bad things that could happen. Nothing that's going to happen this week, of course, we hope. And we have to look at the reason to move off planet, but we do need to move off planet. The smart people in the world have said, it's just Earth is too small and fragile a basket for the human race to keep all the eggs in. I love Robert Heinlein's quote. So we need to move off, and it seems like the dreams of many are getting there. So we should be having some fun there. Okay, why don't we see if there's a few questions that might be asked. Joyce, did you chase down any questions? And we could answer a question or 2.
I don't see anything on the chat list right now.
Okay.
Somebody, I think they can actually state them if they want, or they can write them in the chat list right here.
If somebody wants to unmute themselves and ask a question, that'd be fine. Otherwise, I'll have to jump back in the lecture series here.
Mm-hmm. Well, I have a question. So you have talked a lot about how the dreams of humanity, of at least a few members of humanity, have been an ongoing dream for many years. And yes, it would be fun. I like the idea of going to Mars even. But I think, and I know you're going to talk more about this, but I think there's more to it than just exploration.
Oh,
So
yeah, there's so many dimensions. Yes.
And I think people need to understand that too, that it's not just about, the few of us who would like to explore, who maybe go to other countries, but now we'd like to go to other worlds.
Yeah,
Okay, here's a question from Larry Alos. Most sci-fi stories about space elevators assume a material that is stronger than we have at present. Has this problem been solved? Oh, I know that was a
yes,
big issue that you have
yes.
solved.
I was going to hit that later on when we get to engineering, but the answer is we have a material that's more than sufficient, like 150% or no, 300% more than the required strength and the difficulty. And it's being developed right now in the laboratory in multiple countries. China, the leader from my perspective is University of Manchester in England. We also have around Oak Ridge, Tennessee, a company called General Graphene. It's a whole new material, brand new. Nobel Prize was awarded for the discovery of the two-dimensional material back in, pick a time, 2010, something like that. I mean, it's relatively new material in the overall sense of material science. In fact, books say it can't exist. The textbooks say it can't exist, but no, Nobel Prize was awarded for it. We are currently producing the material at 1,000 meters per 30 minutes in a 1 meter wide swath. Now, that's not exactly the material we'll be using on space elevators, but it's a predecessor, and it's the same techniques and everything else. It's called graphene superlaminate, and it's coming off the laboratory floor as we speak. So a friend of mine who's on our board of directors for the Space Elevator Consortium says it'll be ready easily by the time we need it for 2037 operations. We need the tether to be long and strong by, say, 2033 or something like that. It's not like it's got to be tomorrow. So they're working furiously to take the material we're looking for, which has been developed in small pieces, and they are working to come up with a continuous production process for that material. And the driver is not space elevators. The driver is automobile hoods, airplane wings, structures in space, all kinds of things. I mean, the material really is a material, magic material, and it's well underway. That's about all I can say about it.
Here's another interesting question. This one from Ben Hancock. Who owns the space along the route of the space elevators?
Oh man, now you're going to get into the legal question. There are lots of questions, all kinds of them, but here's my answer. My answer is we have to work with the law of the seas when we put our floating platform on the equator significantly away from any territorial demands of islanders. So, you know, we'll be 200 miles away from any islands and stuff like that. So we have the law of the seas. Then we have the aeronautics law, and we got to make sure that we have notices that it's up there so planes don't run into it. And then we go into space law. Holy schnuggers, nobody knows what's going on there. But the bottom line is to put something at the geosynchronous arc, you must go to the International, the ITU, International Telecommunications Union, and ask for permission to transmit and receive radio waves. The whole purpose is so we don't interfere with the guys on the left and the right. Has no stipulation about what the material or structure is at that location. It's RF, radio frequency approval. So if we get the radio frequency approval, then we're 90% of the way there. And then, of course, the legal guys will jump up and down and say, we got to have other approvals. But that's what we're here for. We're trying to figure out how to do that. The legal question is wide open. But let me give you a little funny note about it. 6 years ago at one of our conferences, a space law professor from Japan came to our conference. Japan's working on the space elevator. He came to our conference and he gave a paper that essentially said that the space legal arena says that if any space component hits an Earth-based structure, the launch country is responsible for that. An example, a piece of debris came down and killed a cow in Cuba. And it was a Russian launch, I believe. So the Russians were responsible for that cow. So the legal expert from Japan said, since our space elevator is attached to the Earth, we would be an Earth structure, and anybody who hit it would have to pay for the damage. An interesting twist in the legal arena. I have no idea whether that would hold up or not. But the legal questions are all out there, and we don't know any answers really in the legal questions. I hope that helps. Anyway.
Yeah.
Okay, why don't we get going again? And then I'm going to quit at 40 or, another 25 minutes or so, and we'll see. So if you've got some questions, toss them in on the chat. We'll go from there. Okay, the space elevator. I've been talking about the dreams and where we're going and all that kind of stuff. Now let's talk about what a space elevator is and how it's going to work. And then we can figure out whether that'll match the dreams. Okay, the new vision for a space elevator is it's a green road to space. Well, why can we say that? Well, we've got a passive 1 meter wide ribbon going all the way out to 100,000 kilometers. And we are going to be there, and we're basically raising everything with electricity. So we're not burning any fossil fuels in the atmosphere, damaging the atmosphere. Now, at the present time, with 130 launches per year, nobody cares about the damage done by rockets, because the counterpoint is we need the rockets to do missions like weather and communications and stuff like that. And humanity is helped by all these missions. So therefore, we need to have those rocket launches. So therefore, we really don't care about the environmental impact. Well, in the last probably 18 months, and it's just the last 18 months, many articles have been published in science journals and environmental journals and college journals that are addressing the damage to the atmosphere from rockets. And it's not trivial. If you only do 130 of them a year, we all blow it off and we don't worry about it. But Mr. Musk has announced he's going to do 1,000 a year to do his flights to Mars. And if Mr. Musk does 1,000 a year, then the Chinese are going to do 1,000 a year. And Mr. Bezos wants to do 1,000 a year, and expand that any way you want. And we're going to get a lot of launches per year, and that might damage the atmosphere tremendously. And so I'm glad there are people looking at that in the sense of we don't want to damage the atmosphere while we're trying to fix it with space solar power and sunshades and stuff like that. So the new vision is we're the green road to space, and we're helping people understand the environmental impact of rockets and the fact that they have a choice. If we get the space elevator up, we don't need to burn as many rockets. So we have an approach which says we're going to work with rockets, dual space access, because rockets are really good other than burning into the atmosphere. And if we can cut that back, that'd be good. But they move people through radiation belts rapidly. Okay, so our vision is green road to space, and it looks something like this. We've got 2 space elevators going up in what we call a galactic harbor, and that's just a term we're using. Commercially, somebody would buy the rights to galactic harbor, and they would own those 2, both up, one down periodically. We don't see much business coming down for a while. And so there'd be 6 of those space elevators. And then we've got the initial operations, which would be about 30 tons per year. Now, wait a minute now, let's put that in perspective. Remember, humanity's only put up 26,000 tons in the whole history of humans in rockets. We plan on, once we get operational, to do more than that per year. So we're really talking about a capability that outstrips rocket capability right off the bat. And then as we grow our space elevators and grow them towards having people on them, so more robust, maybe 2 for each one of the single space elevators, whatever, we plan on expanding the capability of each space elevator to 80-ton payloads, which then results in 170,000 tons per year. Now, you put that in perspective, Mr. Musk wants to do 1,000 launches a year for about 70 years to get to his 1 million tons to Mars. We can do it in 5 years or 6 years. So you can see that the opportunity to lift mass, whether it's early and it's only as much mass in 1 year as all of humanity has done in the history, or the future where we can actually fulfill needs in the dreams that people have had. We're going to move tremendous amount of mass, and we're going to do it in a green manner. How does that happen? The answer is it's a permanent bridge to space. Instead of individual events, it's just a permanent bridge. Think of it as a bridge going across a river. It's that simple. Okay, I showed you that picture before, but it's extremely important to understand that that's a bridge to space. So if you've got, a river and you want business on the other side, you lose little boats every once in a while. Then somebody comes along and puts a bridge across there. Which path are you going to take? Little boats, or are you going to take a big bridge? So the answer is that we have a real philosophy on providing capability. So we call it the modern day space elevator. Since the identification of this new material and showing that the material is real and will be ready for us, we've started calling the space elevator the modern space elevator, because we are actually in engineering development now. We've done some little tests, not big ones. We don't have much money, but we've done some really good studies that show the TRL levels, technology readiness levels, are there for all the components except for the material. We are the green road to space. We want to join the rockets. And because of all this, we want to move massive amounts of cargo to fulfill the dreams of many. So what are the transformational characteristics that we're really talking about? Why is this bridge better than individual events? Well, here's a list of them, and we'll go over them in detail as we go along. But daily, routinely, safely, inexpensively. Oh, wait a minute. Routinely? When somebody launches a rocket, and you've seen this, if it's successful and gets off the ground, goes away, everybody stands up and claps. When you drive across the bridge, do you stop the car and stand up and applaud? I got across the bridge. No, it's different. So what we want to do is we want to transform the way you think about going to space. And then, of course, the economics. Having a permanent infrastructure blows away any other approach to economics. It's remarkable. I've talked about the massive movement. It's Green Road. But here's one I haven't talked about. When we go to Mars, the approach to Mars is we wait 26 months, and then we have a fleet of vehicles. Last time it was 3 vehicles from 3 countries, and they take 8 months to get to Mars. And then you wait 26 more months. This is because of the planetary alignments and the phenomenal requirements for energy. Read that, consuming fuel. So we only have these opportunities once in a while. If we're at the top of an apex anchor and we're going 15,000 miles an hour, 7.76 kilometers, then we can release from that every day of the year. No stinking wait. And we can go to Mars. Now, some trips take 400 days, but some take 61 days, 2 months. So we can have the fast transit with 2 months, and we have the long transit later. So if you're going to send nails and hammers, you send it on the long trip. And if you're going to send pizza, you better send it on the short trip. But the point is, the alignment of planets are drive the time it takes, but not the opportunities. We can launch every day. We've got better design capabilities, and we can assemble at the top of the gravity well. I'll talk about that in a little while. But safely, inexpensively. Now, here's one that's a fun one. On-time launch. Don't even think about it. The space arena doesn't do on-time delivery or on-time launch. It just doesn't do it. The philosophy in the American and Western launches is we launch when ready. Well, that's worked very, very well in the past. We haven't blown up some rockets and stuff like that. Now, the Russians, they're a little different. The Russians, from the beginning, have always developed their systems to be more military. When somebody says you're going to launch on Tuesday, you launch on Tuesday or you get shot, one of the two. I mean, it's that brutal in some cases. So what they do is they design it more robustly and design it to launch every day. Oh, by the way, if there's high-speed upper atmospheric winds, which the Americans won't launch into. The Russians say to hell with it, and they launch because they designed the system to go through high-speed launch in the upper atmosphere, in the upper reaches of the atmosphere. So on-time delivery, some of those things they don't, the rocket guys don't have. So what do we do with our space elevator? We have a bus schedule. We had a study with Arizona State University. It was quite good. And they did the calculations on going from the Earth to Mars over a period. I don't have it marked down there. It's around the 2035 time period. And so they calculated the trip's time and launch and everything else. So we had 6 space elevators, and we asked them to set up a bus schedule. So if you're a logistician and you're trying to support the development of a colony on Mars, wouldn't you like to have a bus schedule? And you say, I need to send the nails on this trip that's 182 days from the Atlantic #1, and it'll reach there in 180. Oh, I got to get pizza. We want to go for the 61 days. Oh, I don't see it on this schedule. And so what you do is you pick it. The logistician on-time delivery is what can be incorporated in liftoffs if you use in space elevators. Okay, now here's the one that's kind of missed. Other people don't see this, especially the rocket guys. We have an economic paradigm shift when we do space elevators. And the answer is we don't care what the price per lift is. What we want to know is what's the economic growth at the other end. It's like when we put a cross-country transcontinental railroad in the 1865 time period. The government gave the developers property along the way. And the development of that property is where the economics came from. The mining and the towns, the farming and stuff like that. The owners sold those and made the money. The price for the ticket on a train was small and didn't make them much money, but all the value was from the economic growth at the other end. And so that's the same thing we'll see in space elevators. So permanent infrastructure. You know, I mentioned this once or twice, permanent, daily, routine, inexpensive, all that kind of stuff. And it's green, and it will beat the gravity well. Here's a chart on the mass and the annual payload delivery, which is really remarkable when you start thinking about our history and what we've done in the past. I mean, it blows it all away. And we mentioned Green Road to Space before. We raise everything with electricity. And also, now here's the other aspect of Green Road to Space. The sunshade to lower the temperature of the Earth by 2 degrees cannot be done by rockets. I don't care what you say. 20 million tons at 4% to low Earth orbit. You know, that's too many rockets. So rockets can't really do this. So we've never really gotten this off the table. But we can do it. We can if we use space elevators. And so literally we're enabling Earth environmental savior projects. That and space solar power, another program we haven't talked about, which can provide base level electricity to the Earth without burning rocket fuel to do that. So we've got a study, anybody who wants to look at it, it's on our site, and we've explained all these environmental changes, and we're passing that around free to anybody who wants it to try to spread the word. Okay, go to Mars. Here's a little picture here. Rotating tether at geosynchronous, we match the speed there, so we just drop off for communication satellites or weather satellites. You go up to 100,000 kilometers, you go 7.76 kilometers per second, 15,000 or something like that, miles per hour. And you can go to Mars in 61 days. You extend the tether up to 160,000 kilometers, you can leave the solar system with no rockets. Wait a minute. Wait a minute, you mean we can go and leave our solar system and not use rockets? Yes, the answer is yes. Now, we'd want to have rockets to kind of guide it, and if we wanted to rendezvous with anybody or add some velocity to get there faster or whatever else, we could add rockets to that. But, you know, just the length would get you there pretty fast. Here's how we do Mars in 61 days. We don't use the minimum energy ellipse, which is called the Holman transfer, which is what we do today. We wait for the two planets to align, and then we use the minimum energy ellipse, which gets us there with the maximum rocket we have. Anyway, what we do is we go really, really, really fast, and we cut the corner. So we make it 61 days across the orbit there instead of 8 months. So it's an energy thing. We can go fast. We can do different things. We can enable different missions. So we can enable these interplanetary missions. This came out of the space, this joint study between ISAC and Arizona State University. 61 days, release any day of the year to go to Mars in massive tonnage. I mean, it's a game changer there. Okay, the rocket fairing. Everybody loves the James Webb Telescope, but it had to be folded into this origami little shape, and then it had to unfold. And I think it had 144 single events that could have caused mission failure. So the engineers had to make sure that every little origami move was perfect and wouldn't fail, because if it failed, then they wouldn't have a mission out there. So we can have tremendous volume. In fact, we don't really need to have sides and stuff. We could stick stuff out in all kinds of directions. It's an unspoken little benefit of space elevators, but it's kind of like pretty real for the designers. Okay, assembly at the top of the gravity well. Let me explain it as a young man did at the university in Stockholm. I've forgotten, KTH or something like that. Anyway, he did a master's thesis. Actually, he hasn't finished the thesis report yet, on astronaut safety in the cislunar arena. In other words, everything past geosynchronous is called cislunar. It's close to the moon. Okay, first off, we have a law that we've all signed around the world that says astronaut safety. If some astronauts are in trouble, whoever they are, the other countries will go help save them. Now, in low Earth orbit, it was somewhat doable, very risky, and you guys have seen how long it takes to launch a rocket. If you had astronauts in trouble someplace, it would be really, really hard to get to them and save them. Now, the commercial guys are a lot better at on-time delivery and all that kind of stuff, so maybe they could save them. But if you go beyond geosynchronous, there's no way that we can save astronauts if they get in trouble with our rocket infrastructure. But let's think about a new idea. At the top of our apex anchor, we have an assembly and storage facility, and we put oxygen tanks and water tanks and facilities like capsules, human capsules, and facilities for the surface of the moon, and a whole bunch of rockets to move them around the cislunar arena so that they can go anywhere they want. And we have an emergency someplace in the cislunar arena, and the astronauts call and say, help, help, I'm in trouble. What you can do is take your assets that are up at 100,000 kilometers with plenty of potential energy and kinetic energy, assemble them into a rescue craft, and send them to the astronauts in trouble. So we can be there in 14 hours. Now, normally a rocket from the surface of the Earth takes 3 days. So not only would you have to assemble a rocket on the ground to respond to an emergency call, then you'd have to find the resources for the emergency. Then you'd have to load them all, and then you'd have to take 3 days to get there, and we can be there in 14 hours. So the assembly at the top of the gravity well has phenomenal transformational concepts, from the ability to have a storage and assembly plant at the top of the gravity well. So it's an intriguing concept that hasn't been thought of by rocket guys, because they just blow through that altitude with the rocket periodically and in trouble and massive consumption of energy. Here's one that is a major program in a whole bunch of countries right now, and they're trying to develop this so that we can replace coal plants and stop global warming. The problem is they need 5 million tons in geosynchronous orbit. Remember, I said you only get 2% of the mass on the pad to geosynchronous, so that's a bunch of money, a bunch of pounds on the launch pad. Anyway, so that's an example of the near-term needs requiring assembly at geosynchronous. So we could assemble at the top of the geosynchronous climb and just do it there at the space elevator, bring stuff up. Okay, let's see. It's probably a good time to stop right now, and we have a question or two. Joyce, do we get any questions there? It looks like there's 7 chats. Any of them questions?
I can help here, Pete, as Joyce is coming off mute. We do have a few questions to share with you.
Good.
So first is going back a bit. You spoke on this a little bit about the structures themselves, but what kind of structures are attached to the tether to actually transport people? What's that look like, and what's that kind of?
Yes. Well, let's talk about the tether climber, and let's put the people on hold right now. The people would be like 15 years after we have the robotic version. The extra safety issues of taking care of people would be a little added complexity. So we're going to do robotics for 10 or 15 years first, but we need to move the stuff up from the Earth port. And the answer is it's a box. That's all it is. And we'll have motors that drive wheels. And the concept is relatively simple. You have a 1 meter wide tether, and you put wheels on both sides. Then you put pressure on the wheels against the tether. You get electricity, turn the wheel, the friction's enabled, and you go up. It's a very simple approach, 2 wheels, 1 on each side of the tether. And so we just finished a 18-month study looking at that particular interface, the tether and the tether climber interface. And it's going to be published within, pick a number, 3 months. But it's a delightful look at what type of friction do we need, what type of material do we need. They came to the conclusion, I believe, that you need the graphene super laminate for the strength and the layout, but it's very slick, so we need to have a material on both sides called hexagonal boron nitride. By the way, that's a 2-dimensional material, also similar to graphene. And so they all match together and they should work. So the friction is an issue. Then you've got to have power. And we figured that if we have solar arrays, we need a lot of them, we'd have enough power to raise it so that the tether climber would go from the surface of the ocean to geosynchronous in 7 days. In addition, we can have 7 tether climbers at 20 metric tons each with 14 metric tons of payload. So you can get a feel that we're really, really thinking about this. Now, the real secret is we have a partner, I have a partner, that comes out of 50 years of doing transportation issues and moving stuff, trains, planes, trucks, and ships. And so he's come into the space elevator arena and has tremendous value to us on understanding what we're talking about. So we've come to the conclusion we need containers that go from the product developer someplace across the country on a train, and then maybe across the ocean on an airplane, and then on a tugboat to the equatorial region. And if you have it in a container, then you have the container get on the tether climber and you go up and you never touch it. So his transportation expertise is helping us understand how we do that. And we're designing the tether climber to match his ideas of containers. So obviously we don't need any shell on the tether climber because we're going to use containers for all our products. So there went a lot of mass. We don't need that. So we've got some interesting thoughts.
Yeah, and Pete, while we're on the subject of the tether itself, so clearly this is not attaching to Earth, it's connecting to kind of a drop location in the ocean, is that correct?
It's on a big, heavy sucker, yes. It will keep it down, yes.
Okay, so then what's it tethered to in space? Would it be connected directly to Mars?
No, no. Think rock on the end of a string as you twirl it around your head, or something like that. What happens is centrifugal force. It's an outward force that keeps the string taut. So what we've done is we've taken a mass and put it at the end of the tether, and we're rotating with the Earth. And so it's being tossed around just like a string around your head. They've done all kinds of dynamic studies on the tether and everything else, and it is so solid, so stable, it's amazing. And the outward force on the tether would be keeping it, taut, and you'd have to have it a little stronger, a little more outward force than necessary, because you're now going to put a tether climber on it that's 20 tons, and it's going to pull down. So if the force upward has to be greater than the pull down force so that you can climb it. Otherwise it comes all down, so that wouldn't work. So you got to have an outward force, and that's centrifugal force. Now, of course, gravity is a bear, so we got to have enough centrifugal force to not only overpower the tether climber going up, but the gravity of pulling, the gravitational force on every element of the tether. So yeah, it's a mathematical equation that shows that you can do it.
Okay. And so assuming that we have this tether that's jutting out, in your estimates, we have 3 different tethers, right, from 3 different ocean locations. How do we prevent or avoid any kind of traffic that takes place in space? For example, airplanes, or what's the health impact of migratory birds or things like that?
Oh, those are all relatively trivial. Every airplane pilot goes into the weather station and looks for NOTAMs, which are notices of "don't fly there, you stupid guy." It's like over Area 51 and over big cities, and you can't fly over an airport unless you're landing, stuff like that. Anyway, we'd have NOTAMs out that says "don't fly here." Well, actually, nobody flies there anyway. It's in the Pacific, 2,000 kilometers to the west of the Galapagos, and there's no flight pattern over there, so I'm not worried about that. Birds and stuff are smart enough; they'll see it. They won't get hurt. Now you talk about space debris. We've got 2 reports. You can go to our website and read them, 2010 and 2020, and they describe the probability of conjunction. Now that's a pretty word that NASA uses instead of collision. But we calculated the probability of conjunctions between all the parts in space, and NASA contributed all the data, and then we did the calculations. And the answer is we can move the tether to get out of the way of the big stuff, and the tether is strong enough it can take all the little stuff. So it'll just either bounce it off or let it penetrate. And then we'll have a little tether climber that goes up and inspects for all the little holes and patches and stuff like that. We understand the space debris environment pretty well, and we understand it. The answer is it's manageable.
Got it. Another question from one of our participants here, Pete, is the climber itself reusable, or does it make a one-way trip? Perhaps it's integrated with a payload system?
Of course, it's going to be designed to be reusable, of course. But then we have to think about operations. My answer is early operations will have one-way tethers, and then we'll use the tethers for extra mass at the apex anchor, so we get more force going outward. That's my guess. I have no idea. And then once we get going and we get operational and we have 6 tethers, what we're going to have is 2 tethers at each galactic harbor. So we have 6 around the equator. I see no reason why most of the business is going to be at geosynchronous, where the commercial demand is, I think. So what we'll do is we'll go up to geosynchronous, dump the payload, and then we'll float over to the next door space elevator. It'd be 200 or 300 kilometers away. And then we'll grab it and we'll come down in groups, maybe 10 of them together, something like that. So we'll bring them down. But when we come down, we've got to stop up our operations for 7 days. So therefore, it's kind of like, are they worth bringing down, or should we use them? An example is they've got good solar cells, so we could use solar cells at geosynchronous for other missions. So maybe we just scavenge what's on them and take them apart. You've asked a very penetrating question, which we have no answers for.
Well, I have one more for you here from our attendees here. How is the electrical energy that you described that's fueling the motors, how is that actually brought to the climbing system if these tethers are not connected to the surface somewhere? Are these using generators of some kind?
No, the electricity comes from the sun. We have solar arrays spread out around the tether climber. So it's purely solar energy hitting solar arrays, providing electricity to drive the tether climber. They're all independent. It turns out that there's a basic problem in that mass is extremely critical in the whole equation, the mass of the tether climber. And so we cannot have inherent energy on the tethered climber, like a nuclear motor or a big battery or something like that. I mean, we have batteries just to handle the electricity, but we don't have batteries storing enough energy to climb 100,000 kilometers. So, you know, it's a design trade space. And until we get $1 billion and somebody decides they're going to build this, the trade space is all hypothetical right now, but we've got so many answers that we know there's one there someplace, so we can make it work.
Okay, we had another question come in here briefly. Pete, talking again about the tethers themselves. Are they permanent physical entities, or can they be removed? How do we establish something that's that long from the start?
Okay, we got to think about the bridges. What you want to do is the same thing. You put it there. Now you'd improve it later or remove it if somebody wants it removed. But I mean, it's just a bridge. How do we put it there to start? Okay, we take a reel of the tether material. Now this would be a preliminary starter tether, not one for production. All you do is you go up to geosynchronous, you run some tether down and some tether up, because you have to keep the center of mass at geosynchronous, plus or minus a little bit. And then you run some more tether down, you run, you know, you reel it out, and then you reel up and reel up. And then you get to the point where the tether's long enough, you grab it at the earth port and you attach it to the reel down there. And then you take the upper aspect of it and you reel it out more and more. So you have the outward force, the centrifugal force. And then you've got a starter tether. And then you run tether climbers up the starter tether that have tether on it. And then we attach the tether to the starter tether in many layers. It turns out one study said we need 267 tether climbers. Another said 435. We have no flipping idea how many tether climbers we need, but we're going to have tether climbers building the tether to be the operational tether. So that's the way it'll be set up and working. And the tether climber is a pretty simple idea. It's just climb up and glue the tether or something. We've got ways to do that. Okay, well, we better get going if I'm going to finish charts. By the way, there's no need to finish charts if we have big questions or anybody wants to interrupt. The answer is we're trying to pass the word on these different things. So the next one is dual space access, the future. And if you remember, I said I really like rockets because they have so many strengths. You know, we can't land on a planet or rendezvous with an asteroid unless we have rockets. Now, the plan overall in space elevator community is to have space elevators on Mars and any other planet we want to go to, because the gravity wells are bare wherever we go. So once we develop the technology, we'd have them elsewhere. Okay, but the dual space access strategy is we leverage rockets and we want to work with them. And it's a very simple answer. They have opportunities and strengths, and we have opportunities and strengths, and we want to work with them. Here's an example of the way it would work. We talked about space solar power a while back, and it's a huge mass satellites. The minimum mass satellite being designed today to do space solar power is 2,000 tons. 2,000 tons to geosynchronous. So we would have to lift, you know, on the space elevator, 2,000 tons. Well, the first ones are going to be put into low Earth orbit as prototypes to check out that we can make them and we can assemble them and all that kind of stuff, because you can't get them there in one launch. So you got to assemble them. And so the first prototypes will be at LEO, and then they're going to put a prototype at geosynchronous using rockets. Maybe the second or third one will be done by rockets by say 20, 30, 35, somewhere around it. Then we'll be ready. So at the end of the prototype phasing on space solar power, we can start lifting the heavy mass. And that's what we mean by dual space access. Let rockets do what they do well until 2037 when we're operational. And then we share the loading. And we do the heavy lifting and they do the sophisticated stuff and move people and stuff like that. So that's the idea on dual space access. We leverage their strengths and we do major programs that way. And these are just words that build that out. So anybody who wants to check out that chart later on. Okay, where are we? This is a puzzle. Everybody says this is brand new. I never heard of it, you know? And so let's talk about where we are. In 2002, NASA hired a Dr. Brad Edwards to design space elevators, and he did a spectacular job, and it really set off everything. And he set up the whole thing, but he didn't have a material. And so we were on hold at 2002 when he came out with his reports. Over the next 5 or 6 years, we created ISIC and we did a bunch of other things. And then in the middle of the 2010 decade, we actually had major studies completed that looked at the technologies for space elevators. And we came up with the final answer that we could build anything in a space elevator except for the tether. Well, about the same time, the tether material was discovered and the Nobel Prize was awarded, and they started working on this tether. And so we have all the engineering aspects of the tether components, tether climate components and everything, all understood. We could do the earth port today. We could do the apex anchor today. We could do almost everything we need to do, headquarters and comms and communications and all that stuff today. No sweat. We have to figure out how to build the tether and make it long enough and strong enough and all that. We've got a ways to go, but we're in the middle of the engineering validation phase. Then once we move out of that, we move into the design validation. That's where all the testing leads to final designs and final material. And then we move into mission ops. We're in the middle of this blue box someplace, the second blue box. So we're well along the way. Here's a plot on strength and density of material. And you can see all those old things. That's all old thinking. And then we had CNTs, carbon nanotubes, come up in Dr. Edwards' time period. And that's what was a great promise. So everybody charged off on space elevators because we had a material that might work. Well, it was overrated and has fallen short of any capability. So now that graphene came along, the Nobel Prize was awarded for it and everything else. This level of strength versus density is what we need for space elevators. So we now have a material that would do it. Now, by the way, since they discovered graphene, that's what the Nobel Prize was awarded for. They found about 40 other two-dimensional materials that have similar strengths and similar characteristics. So it's not just one material we're depending on. It's the category of a new material, and all of them have different characteristics, like hexagonal boron nitride loves the space arena. They don't worry about oxygen or anything else. And so that might be the material we end up with. So graphene is strong enough and is the principal candidate right now for it. This is a production line in Kentucky, I think, somewhere around in there. General Graphene, 100,000 meters squared production in a year. Now, this is what's called polycrystalline graphene, which is one level of expertise or strength below ours, but it's the same production idea for the single crystal graphene and the polycrystalline. So we show this as we're making tremendous progress in the concept of how we produce the material. And this is a little pretty picture of it, a whole bunch of strands, 100 million kilometers long, 1 meter wide. We'd have like 14 microns thick on the whole activity and like 12,000 layers. So we understand the material and the strength and all that kind of stuff. Here's our schedule that is basically saying we can be ready by 2037, something like that. And all those things on the left are just phase points of what we have to do. And having been through mega projects, these charts are done and then they're adapted as you go along. So The answer is we think we can do it by 2037. And if it's a little bit late, it's a little bit late. But anyway, now we've done a whole bunch of studies in the International Space Elevator Consortium. You'll see the Green Road to Space, and then the Transportation Story of the 21st Century was the one we did with the ASU, and the survivability ones are in there. So we've got all kinds of background there. And then there are reports down at the bottom that were quite comprehensive and looked at space elevators. The one by Obayashi Corporation actually designed a space elevator for humans. So they took the next step up in difficulty and had two tethers next to each other as principal and backup attached. So you had the tether climbers using two tethers instead of one for safety. Just different design criteria. If you walk into your design process saying we need humans, you come up with different answers than if you say you just need robotics. So why do we need space elevators? The answer is we must. Not only to fulfill the dreams of your granddaughters, okay, we might be a little past our dreams. But anyway, the dreams of our grandchildren are out there, and we can help fulfill them with our space elevators, like take care of the atmosphere, work on going to the moon and Mars, things like that. So we have capabilities that rockets just can't do. And why is that? It's simple. We beat the rocket equation. We are able to deliver 70% of the mass on the pad to geosynchronous and beyond, and the other 30% is a tether climber and can be reused, instead of 0.5% to the stupid surface of Mars. I mean, statistics like that will eat you up, and that's bad. Okay, well, that's the presentation we have. Let's see, we have 11 minutes left, son of a gun. Do we have any more questions or comments or anything like that?
We sure do. Thanks for wrapping things up, Pete. But we do have a couple of questions that were left over from the last time. And then, of course, anyone's happy to add additional questions. You can add them to the chat window here. But let's start with this question here, Pete. Any estimates or guesstimates on your part of the tension the tether will be required to withstand to hold itself in place?
Yes. Oh, you want an answer? Basically, it's between 35 and 37 gigapascals is the tensile strength that we need. And the tether material is promising 150 gigapascals of capability. So that's what, 5 times, something like that. You know as well as I do, when we get going, the requirements will go up and we'll need safety factors and all that. So I'm glad the material is promising such a large number. And by the way, it's not just graphene that's come up with these numbers. Hexagonal boron nitride was recently tested 100, I think it was 130 gigapascals or something. I am not an expert in that area. I leveraged the guys at the University of Manchester in a place called Graphene Engineering Innovation Center, the GEIC. And they're doing really good jobs, and they're actually producing graphene superlaminate and very small parts. They don't have a meter wide sheet or anything like that yet, but they're working on that type of stuff. So yeah, we need strong material that would blow away anybody in the past. I mean, just nobody's ever comprehended anything that strong.
And then just to confirm what you said before, it's centrifugal force that actually keeps the tether in place and keeps it from either falling to Earth or getting lost in space, correct?
Correct.
Okay.
It's the outward force of the rock in a string, yes.
Okay. And you mentioned that the purpose of this would be commercial. So do we need to have a base on Mars or have another location up in space that we're as a destination point, or is this would this serve some sort of exploratory purpose as well?
Yes to that one. That's the answer is, I mean, the blatant question you're asking is, who the heck is the customer for a commercial venture?
Right.
And the answer is relatively simple. Anybody who wants to use a bridge to space instead of a rocket. So all the missions that we've been putting up to GEO and beyond all should use space elevators. Now, when you get people, then you've got radiation belts to go through rapidly, and you want to be safe and you want to do all that kind of stuff. And so I see people as a special thing. If you want to go to low Earth orbit, we don't do low Earth orbit. We're diddly squat. So, you know, you need rockets to go to low Earth orbit and mid Earth orbit, stuff like that. We basically are designed for geosynchronous and beyond. And there's a tremendous need at geosynchronous for big satellites, like for weather and for communications and things like that. Not even to mention new missions that might come about when you get there cheaply, easily, and daily. And then we've got to open up Mars. We can toss supplies to Mars routinely. So that million ton requirement is easily taken care of. And anybody who wants astronaut safety or things like that, you know, capabilities that cannot be done with rockets, we can do. So we're going to transform the environment. And our biggest customer, which we can't say, is Space Solar Power. Space Solar Power wants to stop global warming and reduce the temperature in the atmosphere. And they show that they could be pretty close to do both of those. But it's going to take $40 to $60 billion to do that. And so they're out asking for that in all the countries. There are plenty of programs right now asking for that. They cannot ask for another $20 billion to build the space elevator because their plan doesn't include building space elevators. So we believe that the space solar power community will get their money in the next 2 to 3 years. By then, we'll be starting our engineering development. And then along the way, they're going to say, we need this lift capability and we'll bid on it. That's one of the things we'll do. So I really see space solar power as our big tenet early on. But that doesn't say all the others go away. They're just, the biggest tenet will be moving mass to geosynchronous. Remember, rockets can only put 2% up there. Even if they're reusable and reliable and launching 1,000 times a year, the rocket equation explains you can only put 2% of your mass there.
And I know your point at this stage is to get the word out of utilizing space elevators as opposed to rockets. What is it that we can do directly now to support your mission outside of a financial component? Is this something that we or you have set up a lobbying network that we can get involved in, or what are you calling on the public to do today?
Okay, that is a very big question, and we're in the process of trying to answer it, and we will keep your phone number for sure. But there is something to do very soon, and it's called the Space Elevator Challenge, Improving Humanity's Future. And it's a challenge to students to write essays about space elevator missions and how it would change the future. So it is literally a student challenge that you could spread around in your school and let, you know, students participate. There's obviously a prize, $2,000 for the first and all that kind of stuff. And I would love to send you a copy of that. We haven't released it completely, but 15 October is our release date, but I could ship it to you early on and you could see if you can spread it. We're thinking about the Students for Exploration Development of Space. There's a chapter in many universities. I don't know if you guys have one, or if you have some other club or a physics department or a, you know, mechanical engineering department, or, you know, however you would like to get the word out to students to have an opportunity to compete for an award and to contribute ideas on space elevators.
Thank you. With that, Pete, I want to ask if anyone has any final questions, they can submit them in the chat. And I know Joyce was trying to get back on here. Joyce, I'm sorry, there was some feedback coming from your microphone. If you want to try to get on again to help close us out here.
Okay, do you still have the feedback?
We can hear you okay. You're a little pixelated, but we can hear you. So if you want to close class, that'd be great.
Okay. I was just wanted to say that I think I've read most all of the articles that are available on their website, but I am not a physicist. I'm not a scientist or an engineer, And what you said today with the, with the information, with the visual aids was extremely helpful to me. And I'm hoping that we can even share, this information with others, because it just amazes me what you know. I am so impressed with it, the possibility that if I could go, if you need somebody to volunteer, I'm there.
Yep, I'm there. Yeah, well, thank you, Joyce. It turns out that I believe we have a heck of a message, and we've got to get it out. And you're perfectly correct. We need to spread the word, but we're very close to starting a program to do that.
Wonderful. Yeah, you take it over.
Well, I just want to thank again Dr. Peter Swan for joining us all the way from Arizona. Thank you for making your trip to Holland here as easy as possible. And thank you all for joining us. You should have an evaluation in your email here very shortly. And if you have any questions, please feel free to let us know here at the HASP office, and we'd be happy to relay those to Dr. Swan.
And if you want to pass the questions and stuff like that on, I can reply. You've got my email. You can spread the email out to other people if you'd like, if they want to continue the discussion. It turns out this is a huge area that we have a lot of background on, having done this for a few years. But it's so exciting, and there's so many possibilities. And, if you'd like to use it in some of the academic arenas, I can support that. I currently lecture at Arizona State University in the space system engineering and in the orbits class. So I've got a little bit of credibility here and there to be inside a classroom.
Well, thank you, Pete. We appreciate it. And I hope you all have a wonderful rest of your Tuesday afternoon. And again, just a reminder, Fall 2 registration kicks off next week, a week from today, on October 18th, for more solar system classes, including those that we mentioned at the beginning, our future of our solar system and solar and climate challenge policies. So please stay tuned for those. Hope you have a great rest of your day. Take care.
Okay, thanks, and appreciate it. And anytime you need to talk, let me know.
We appreciate it. Thank you very much, Pete. Take care.
Okay.
Yep. It was